Thank you for the invitation. Sorry not to be visiting in person, that would be more fun. But in any case, I'm happy to tell you about the very large black holes which exist in the early universe and how we think they might have formed, which is one of the interesting research areas I've been pursuing. So I'm starting with the slides in the beginning where you see two images. One represents the distortions of space-time due to a black hole, and the other is an image which was taken of a black hole in a nearby galaxy in a radio interferometry observations. So this demonstrates the idea that black holes don't just sit in vacuum. They actually have some plasma which can swirl around them and light up the black holes so that they become visible to us. I just want to make this distinction a little more clearer even. So physicists, there's arguably something like a physicist black hole. The physicists think of black holes quite differently from astrophysicists. A black hole, basically the concept is really a prediction from Einstein's theory of general relativity, which predicted early on that gravity pulls arbitrarily large mass together to an arbitrarily small region. And in fact, the equations put forward by Einstein was solved very quickly after publication of general relativity by Karl Schwarzschild, while he was serving in the First World War in the Russian front. So these are solutions to Einstein's equations. The resulting concept was actually referred to as Schwarzschild thought or various other terms until about 50 years ago. So the concept is 100 years old, but the name black hole is only 50 years old. And I think everybody knows that the black hole is defined to be some object that's so compact that the escape velocity, if you're very close to it, becomes larger than the speed of light. And this radius for the sun would be 3 kilometers. So if the sun was to collapse to a black hole, this so-called horizon would be 3 kilometers. If you're much farther than 3 kilometers for a sun-sized black hole, then it doesn't look very exotic. But if you're approaching a few kilometers, then you start to see strange effects. So physicists ask various questions, like what happens to stuff that falls into a black hole? What happens at the so-called singularity? Clearly the infinite density doesn't make any sense. Does information actually get lost when stuff falls through horizon, or does somehow information get preserved in the escaping radiation known as Hawking radiation? And actually physicists are also wondering whether general relativity, Einstein's theory, is indeed the correct extension or a complete extension of Newton's theory of gravity in very strong regimes of very strong gravity. Now, separate from these, there's another interesting question, which actually interests astrophysicists perhaps more, and people like me, which is, do black holes really exist? I mean, just the fact that Einstein has a beautiful theory and that there's a solution to the equations, which implies something like the black hole, it doesn't mean nature is obliged to produce these objects. So whether black holes really exist is maybe a question that belongs to astrophysics research. By the way, I'm not sure what these yellow lines are on my screen. Somebody's drawn some lines. Anyway, the astrophysicists think of black holes quite differently from physicists. So rather than distorting space-time, we imagine that there's a lot of plasma around black holes, and they generally tend to swirl around the black hole, as illustrated in this cartoon picture. This is just a cartoon image. So ignore the structure here on the horizon. The main point is that there's stuff that's swirling in and falling towards the black hole and eventually can cross the horizon. and that this stuff is actually very, very hot because it's near the horizon, moving close to the speed of light. So the fact that black holes can light up actually allows us to see them with telescopes. But let me discuss just in general the kinds of black holes we know exist, and then we get to my question of the largest ones, which are the earliest in the universe, and how they came about. So first of all, we know that black holes, very small ones, form when massive stars exhaust their nuclear fuel. The stars shine by nuclear reactions, and so the energy supply is finite. Once all the fusion has happened and the energy has been exhausted, then if the stars were very massive, roughly 25 times the mass of the sun, then they cannot be held up against gravity and they collapse to a black hole. Now this is not known theoretically, but we actually know from observations that these so-called stellar mass black holes exist. In fact, they've been long known to exist in our galaxy, and now recently we know they exist beyond our galaxy. And in fact, in our galaxy, well, let me just show that there are two ways actually of seeing these stellar mass black holes. And curiously, we see them only when they're in binaries. And so there's an image here which shows all known stellar mass black holes. The purple ones here were discovered in traditional astronomical observations. The blue ones have been discovered by LIGO, the gravitational wave detector, which I'm told you had a talk, a lecture recently about. So let me just say that the so-called electromagnetic black holes, they're detected. There should be in our galaxy about, well, millions of these, because our galaxy has tens of billions of stars, and some 1% of stars are massive enough that when they die they become black holes. The problem is we can't see them when there's just one black hole sitting in our galaxy. But this image shows that the swirling gas picture I showed before applies if the black hole has a companion star. So here in this image you see something that's called an X-ray binary. There's a black hole here of, let's say, 10 solar masses left behind by a star that died over here. And there's a neighboring companion star from which material is flowing towards the black hole due to tidal forces and forms this so-called accretion disk. And now this black hole becomes visible to X-ray observations because it's emitting a lot of photons from the hot gas that's swirling around here. And so the purple points here are all such X-ray binary observations. And as you can see, there are millions of black holes in our galaxy, but we've only seen about 20 of these because they have companions and they're being spotted by X-ray telescopes. Now, there's actually recently a deluge of, as you can see, about 50 other stellar mass black holes, which were detected by the LIGO and Virgo Observatory. I'll come back to this later in my talk. But essentially, these black holes don't have to emit any photons. They're just two black holes swirling around each other, and they actually merge due to the emission of gravitational waves. So this is just an image illustrating the space-time distortions, which are dynamic and propagating away from the merging black holes, and have been discovered and by LIGO, and we've tabulated these black hole binary mergers. And we've seen 50 of them, and the largest one actually is here. You can see the way this visual is presented. There's an 85 solar mass black hole here, and the 65 solar mass black hole here, and they merged and formed a 160 solar mass black hole. So there's also neutron stars, but let's ignore those for this talk. So that's it. So we know there are stellar mass black holes. They exist uncontroversially, and there are many of them in our galaxy. Now, in our galaxy, in fact, that's not the end of the story. We also know for sure that there's a 4 million solar mass black hole at the center of our galaxy, of course. Called the galaxy is called the Milky Way, where we live. And the Milky Way looks something like this. This is an image of our neighbor Andromeda galaxy. So just to orient you, I'm showing, of course, we can't take a picture of the Milky Way because we're sitting inside it, but this is a very good illustration how the Milky Way would look like from the outside. It's a very similar galaxy to our neighbor, Andromeda. There's a swirling disk of stars. This is what I alluded to. There's billions of stars in this thin disk going around the center of the galaxy. We're sitting out here, about 20,000 light years from the center. The center has about 1 million stars in a very compact configuration, forming the so-called bulge. And then in the very center of this bulge is what we think is what we now really know is a 4 million solar mass black hole. So I'm sure you heard about this because, in fact, this won the Nobel Prize this year, a few weeks ago, in physics. So these 3 individuals were awarded the Nobel Prize. Roger Penrose for the discovery that black hole formation is a robust prediction of relativity. And then Reinhard Genzel and Andrea Ghez for showing that there's a supermassive black hole at the center of our galaxy. So I want to take 1 minute to explain how we know this. This image here on the left represents an image taken with the Keck telescope, which is a 10-meter telescope sitting in Hawaii. And these colorful blobs are individual stars labeled SO1, SO2, SO3. They're individual stars. They look so blurred because of just how the telescope blurred and the visualization. They're actually just points. They're basically stars. So that's an artifact, but their locations are precisely measured. This here is a center, and this image, as you can see here, was taken in 1995.5, which means June of 1995. Now, just to say one more thing, there's an arrow here which says 0.05 arc seconds. So this is an angle extended on the sky. So this entire image here is extremely tiny region of the center of the galaxy. So 0.05 arc second, which is the size of this arrow, is roughly the angle. If I'm sitting on my chair here in New York City, it's about 0.5 meter. The size of my chair is about 0.5 meter. So if you looked at it from where you are in India, it would extend about 0.05 arc second. So we're talking about an angular region on the sky corresponding to this ridiculously small angle. And then nevertheless, they were able to resolve the motion of these stars. So this is actually a movie. And they kept observing these stars for 25 years now. And you can see that these are observations from 1995, 2000, 2001. I don't think this will go all the way to today. We'll stop the movie, but you can see what happened to the orbits of these stars. They basically follow ellipses. So these 3 particular examples here, this actually ended in 2013. This star actually has completed its orbit in the meantime and has passed the pericenter. But what you can see here is there are 3 examples of these orbits. They're all ellipses. And the focus of the ellipse is at one single point, consistent with the fact that these are just Newtonian orbits, basically, going around the point mass. And then you can calculate the point mass that's sitting there from extremely simple physics, which I'm sure all of you would know how to do. But just to make sure I write here the simplest case. So suppose there's just a compact point source at the center of the galaxy, and then there's a star going around, and let's say it's on a circular orbit. Then you know that the gravitational force is just gm over r squared. The centrifugal acceleration is v squared over r times the mass of the star. So for a circular orbit where you equate these two, you can rearrange this equation, and you can say the central black hole mass over here equals the radius of this orbit, and then the velocity squared divided by Newton's constant. Of course, this is a little more complicated if it's an ellipse and if it's projected along our line of sight. But the main point here is that we can reconstruct the orbit, because on the right-hand side of this equation, everything is measured. When you measure the velocity of the stars, you could see that we saw the orbit completing itself over time. So we know how fast this star is traveling, and we also have the component from a spectrum due to the Doppler shift. We also have the radial velocity. And we also know how far away is the center of the galaxy. So we know r and v squared, and we can calculate m. So you can correct this equation for elliptical orbits, which are in general orientations, but they all give the same answer. So there are about 10 or 15 stars where you get the same answer of 4 million solar masses, with an error of only, as you could see in my previous slide, is about 10% error. And now the question is, what about, so that's extremely convincing, but that's very special because the center of our galaxy is very close to us. So can you tell there are black holes in other galaxies? And the answer is yes. In nearby galaxies, you can do something similar. We can't actually image individual stars and their motion in any other galaxy other than our own. But you can take an image of a galaxy like shown here. And this here is a spiral galaxy, and there's a bunch of stars in the middle, just like the Milky Way. This is a so-called elliptical galaxy, and you again have a bunch of old stars swirling around the nucleus. So you can't resolve these stars, but you can measure the aggregate light of these stars, and you can measure the Doppler velocities averaged over all these stars, and you can see that the motions are very rapid. And so statistically, you can still measure notice the presence of a black hole, which created these very large velocities. Again, now it's not an individual star, but it's a congregation of stars. And for about 100 galaxies, which are close enough and large enough in angle, you can resolve the bulge sufficiently accurately that we can infer the mass. And for these 100 galaxies, for every galaxy where this is in practice possible to do, we find that there is a black hole, and the mass of the black hole is between 1 million and 1 billion solar masses. So that's very interesting. The next question is, okay, well, these are still very nearby galaxies. What about other galaxies in the universe? We know there are very many galaxies, and they're very far from us. The question is, do they also have central black holes? And so here I'm returning to my picture, and this is a different technique to infer the presence of a black hole. And notice that in my previous slides over here, I didn't actually use the fact that the black hole is emitting any radiation. We just used the motions of test particles, here stars, or sometimes some gas around the black hole. But now, when you go to very far, what can reveal the presence of black holes is the fact that they shine. So I showed you this picture, so I'm returning to this picture. So when there's a massive black hole in the center of a galaxy and is being fed copious amounts of plasma, then this is called a quasar, and about 1% of galaxies act like quasars. So the most important fact about quasars for us here is that they're extremely bright. So that's somewhat paradoxical. They're black holes, but they're actually extremely bright. The reason they're so bright is that they generate a lot of energy. So for comparison to a star, imagine that you burn you have a proton inside the star, and it produces some energy by nuclear fusion. Then generally we release per proton an energy that's corresponding to nuclear binding energies, which is about an MeV per proton. Now, if you take the proton and throw it into a black hole, and it accelerates to the speed of light before it's swallowed by the black hole. So here comes a proton swirling around and is going at the speed of light, and then finally falls to the black hole. You can, in principle, lose a lot of this proton's rest mass energy into radiation, because through collisions with other protons, you can tap the entire rest mass. Now, the rest mass of a proton is a giga-electron volt, 900 MeV, so about 1,000 times larger than the nuclear binding energies. So even if you extract 10% of this energy, which we think typically is the case, so 10% of the proton's energy comes out as radiation, 90% contributes to growing the black hole's mass. So if you do that, you still have an engine which is 100 times more efficient than a star in producing radiation. Or a star is basically a nuclear bomb. It's just working by fusion. So because of this, these black holes in centers of distant galaxies can be extremely bright. In fact, they were first spotted in the 1960s, and they're so bright that they outshine their entire galaxy. The host galaxy of the black hole is invisible with the telescopes that existed until recently, and essentially until the Hubble Space Telescope was launched. And so people originally thought they were individual stars in our galaxy, but then they took spectra and revealed their very large Doppler shift and the fact that their spectra looked nothing like a star. And they were named quasi-stellar objects, but this name stuck, so they called quasars. And it was realized from their spectra that they're extremely distant, extremely luminous object. And nothing can produce this much luminosity as far as we know, so it has to be a massive black hole. Now, how far away can we see such galaxies? I should say that of all the galaxies, roughly 1% act like this. So 99% of galaxies are quiet. They might have a black hole in the center, but they may not shine, so we can't tell. But 1% of galaxies have this quasar behavior, and this shows here, and because they're so bright, we can see these quasars to extremely large distances. Which is why my title is the monster black holes at the edge of the universe, because the edge of the universe, of course, is the largest distance to which we can see, and we still see these quasars. So this image on the screen is actually a catalog from so-called Sloan Digital Sky Survey. This was a survey of basically half of the sky, so it's extremely large area covered by observations which extend to large distances. So every dot in this image is a galaxy, is a slice on the sky. So meaning that the radius, the radial coordinate here is the distance away from us as measured from a Doppler shift and the spectrum of each galaxy. And then the polar coordinate here is just an angle on the sky. So we see this is a slice in a big circle on the sky. And you see that there are many galaxies. I don't know if people know what the meaning of redshift is, but this image actually extends to about 10 times, the data extends to about 10 times further than shown in this image, to about 13 billion light years away from us, which means we see about back to the time when the universe was about only 1 billion years old or less. Because its current age of the universe is 13.7 billion years. So we've actually seen back 95% back to the time back to the Big Bang. And these quasars, because they're so bright, they're visible out to these distances. So in fact, the record-holding quasar is sitting in the universe when it was only 700 million years old. I'm going to skip this slide. So in summary, the observational situation about black holes is we know there are stellar mass black holes, we know there are nuclear black holes in the centers of galaxies nearby, even though they're quiet and they don't emit light or don't emit much light. But we also know that massive black holes up to 1 billion solar masses existed when the universe was extremely young. So now I can turn to the question of why that is so surprising. So, okay, I mean, it does sound interesting. Huge black holes exist early on, but why is that actually a puzzle and requires some thinking? So then I have to switch gears and tell you a very concise 2-minute summary of the history of the universe so that you appreciate the problem. So this chart here is showing the Big Bang, which happened 13.7 billion years ago. This shows here the present day universe. So as the universe is expanding, its density is dropping and it's cooling, and we have some information about the universe when it was actually quite young, about 300,000 years old, by the observations of the so-called cosmic microwave background, which is you can think of that as an afterglow of the Big Bang. And we see this radiation emanating from a 300,000-year-old universe. And for my story, the important point is that we see this little colored image shows the pattern of this radiation on the sky and the fact that it's fluctuating. But it reveals to us that the density was extremely uniform. The universe was very small, well, was quite hot, and was extremely uniform. The density fluctuations were 1 part in 100,000 fractionally. So there were certainly no galaxies or black holes or stars or anything present in the universe at that early epoch. Now, unfortunately, then we don't have direct observations. This radiation from 300,000 years just travels to us more or less without interacting with anything until we detect it with our telescopes here on Earth. So we have a deficit in observations called the cosmic dark age or dark zone. But we do have the telescopes which are looking in the other direction from now back in time or out to large distances. And they revealed currently, as I already said, the objects which exist at 700 million years old. Now, we'll soon have some extension of our observational horizon by the James Webb Space Telescope, which is the successor of Hubble. So we can probably partially lift the curtain on this dark zone and look back to when the universe was about 100 million years old, when we think the first stars and galaxies might have formed, as I'll explain in a second. So our theory says that there was no structures in the universe when it was very young, and then by 700 million years old, apparently there are these big black holes. Now, why is this puzzling? It's essentially, as I'll explain, it's because the time is short. So now I have to explain to you, again, in very rudimentary way, how we think the first objects formed in the universe. And essentially, we know this quite well from theory. So this is all theory. We have not observed these very early first objects. And but nevertheless, we have a very well developed understanding that the first, I will here call them protogalactic clouds, appeared at about 100 million years after the Big Bang. And so by protogalactic cloud, I mean a cloud which was slightly overdense than the rest of the average density of the universe. And you can actually think about this yourself and conclude that there's something called a gravitational instability, because suppose the universe was expanding and was perfectly smooth, then nothing would happen. There would be no structures. There would be no reason for one place in the universe to be different from another. And the universe would then be an eternally expanding uniform plasma. But we do know from the microwave background that there were fluctuations, even though they were tiny. And then if you imagine that you're sitting in a region of the universe which is expanding, but is slightly more dense than average, then the neighboring regions will feel more gravity towards the center of mass of this overdense region. So they slow down their expansion compared to the rest of the universe. And therefore, that overdense region now become even more overdense, and then it's even more pulling extra force on its surroundings, and then it becomes even more overdense, and this runs away and creates what's called the gravitational instability and the collapse of clouds, which separate from the expanding universe, and eventually not just slowing down their expansion, but completely turn around and start recollapsing towards their center of mass. So we actually quite well understand that this happens at 100 million years after the Big Bang. And these first collapsed clouds contain about less than 1 million, maybe 100,000 solar mass of what I call gas, which I'll explain in a second. But it's certainly not a galaxy or a star or a black hole. It's just a collapsed cloud. Now the problem with this cloud is that its density in general is extremely low compared to that of a star or any astrophysical object. And that's because when the cloud is collapsing, after it's separated from the expansion of the universe, its density is increasing, but so is its temperature and pressure. As you very well know, when you compress something, then its pressure will rise. So I just have a silly example here of a bicycle pump. The air in this pump, when you compress it, it heats up. You can feel the pump getting warmer. And you can also feel that the pressure actually makes it very hard at the very end when you're pushing the pump downwards to, I hope you all have bicycles and tried this. When you try to inflate the bicycle tire, initially it's very easy. The air is compressed very easily, but at the end when the pressure has risen, it becomes impossible. So the same thing happens in this case. It's gravity, not your arm, that's pushing and making this cloud dense. But the analogy is very, very accurate in the sense that here gravitational force compresses the cloud, pressure rises, and halts the collapse. Now, that makes it impossible to form a star. So how do stars actually form? Because this is essentially the process stars form in our own galaxy. So the way you evade this is that you deflate the pressure. So deflating the pressure means you need to somehow get rid of the rapid motions of the constituent atoms in your gas. As you know, that pressure is essentially nothing more than the random motions of the molecules of whatever gas you're dealing with. So high pressure means the gas has a high temperature because the molecules are moving very rapidly. So nature solves the problem of contracting and making very dense clouds by what's called radiative cooling. So you should imagine there are these molecules which make up the gas, and then they collide because they travel at very high velocities. They suffer violent collisions or violent interactions, near passages of each other. And I'm sure most of you have taken quantum mechanics, and you know that molecules have discrete energy states. So when two complicated molecules pass each other or collide, they excite, they start in response to the interaction, vibrating or rotating, or the electrons move to a higher energy level. And so effectively then what happened was you took two molecules and you converted their velocity. So they slow down, and the energy, which was originally their velocity, is now stored in the vibrations and rotations of the molecule. But then soon afterwards, the molecule doesn't like to be in these excited states, so it goes back to its original non-vibrating, non-rotating ground state and emits a photon. So the net effect is that you've collided two molecules, or can even be atoms, and you went through this excited quantum state, but you've converted kinetic energy to a photon, and the photon just leaves the cloud. So you're continuously extracting temperature, lowering the temperature and converting it to radiation. And the way this happens in our galaxy is very efficient, because this is the periodic table here. And in our galaxy, most of these elements are present. And actually the main molecule which does this cooling to enable the formation of stars in our galaxy and in other galaxies is carbon monoxide. So there's a carbon atom and an oxygen atom, they form a molecule, and they are very efficient agents of this radiative cooling. And here comes the problem that, as you might have heard, in the early universe, where we have not yet formed any stars, we're trying to form the first generation of stars in these collapsing clouds. The periodic table actually looked very different. It looked like this. There was hydrogen and helium, which was fused just minutes after the Big Bang. But then, unfortunately, fusion stopped. Unfortunately, if your goal is to have these efficient radiative processes, then it's unfortunate that fusion stopped. And that's actually also extremely well understood. Basically, for fusion to happen, you need densities and temperatures comparable to the core of the sun. That's how you you must smash together hydrogen atoms with energies corresponding to the nuclear binding energies of MeV. So you have to have billions of Kelvin temperatures. And the early universe had these billion Kelvin temperatures and high densities, but then as it expanded, it cooled below 1 billion degrees very quickly, within a few minutes after the Big Bang. So fusion basically stopped. After a lot of hydrogen was fused into helium, this process just stopped. It's very different from a star, which is living there for billions of years. So you have a lot of time to fuse other things, and then pollute the rest of the universe. So all the carbon, oxygen, and other elements came from stars, which fused them over billions of years. And in the early universe, that didn't happen. So we have only hydrogen and helium. And now that's very interesting for us, because now you have to ask, can you still have radiative cooling so that the gas cloud can continue contracting and form a star or a black hole? So the physics here is something that I've been specializing on over my career, and this has to do with radiative cooling with hydrogen molecules. So as I said, there's hydrogen and helium in the universe and in the early times. So you can't have carbon monoxide, but you can take 2 hydrogen atoms and make a hydrogen molecule. And this hydrogen molecule can actually do this radiative cooling. It has rotations and vibrations, but so it's actually possible, which is good. On the other hand, it's much more inefficient. Its energy levels are much higher up than for carbon monoxide, so you have to have much hotter gas in order to excite these quantum states. So it's overall an inefficient way of doing this radiative cooling, but it's possible. And because it's so inefficient, so the main difference actually, that in our galaxy, when stars are forming, carbon monoxide deflates the pressure and cools down the molecular gas to temperatures of just a few Kelvin. So it's extremely cold, and it's very prone to, it doesn't have much pressure forces, so it's very prone to gravitationally collapsing into small stars. In the early universe, you have to excite the hydrogen molecules quantum states, so that only happens when the gas temperature is much larger, 100 Kelvin. And that means that it's much less inefficient in gravitationally fragmenting into stars. So it's quite well understood now that the first stars, as a result, were very massive. They were very different from stars born in our galaxy. They were very massive. Maybe characteristic mass is 100 solar masses or so. I mean, this number is not, again, this is all theoretical calculations, and this debates exact numbers. But the general conclusion is that they're very massive. And the other general conclusion is that massive stars are very short-lived. They only live for a few million years. So this is now becoming very promising, because this theory, the bottom line for us, is that just after about 100 million years in the universe, there appear these million solar mass clouds. And in these clouds, hydrogen molecule forms. The temperature in the clouds become a few hundred degrees, and maybe one or a few massive stars appear in these clouds. And after just 1 million years, they die. And I already told you in the beginning that massive stars, when they die, they leave black hole remnants. So far this is promising. As again, our goal, to remind you, is we want to manufacture billion solar mass black holes by 700 million years after the Big Bang. But now we at least know that 100 million years after the Big Bang, we will have 100 solar mass black holes in existence. I think I'm going to skip this. So how can you then proceed and use this kind of knowledge that we have these stellar mass black holes to make supermassive black holes? So there's, generally speaking, if you were just chatting among ourselves, you would say, well, there are 2 ways to do that. One is you take one of these stellar mass black holes and you feed it a lot of more gas, and it will grow eventually to 1 billion solar masses. Or another way to do this is, well, maybe merge together many of these stellar mass black holes into a giant supermassive black hole. So let me explain the difficulties with both of these scenarios and how I think we can solve those difficulties. So let's start with the first method. So let's say you have a stellar mass black hole and you're trying to grow it very rapidly. So I don't know if I have the picture here. So actually, let me go back to my picture, which I showed here. So now we're talking about having a stellar mass black hole. Some rest of the gas cloud in which this black hole was born might be swirling around and trying to fall into the black hole and therefore increase its mass. And so here's the problem with that scenario. Is that, as I just explained, the general expectation is that 10% of the rest mass of the gas falling towards the black hole is converted to radiation, and 90% would fall into the black hole and contribute to what we want, increasing its mass. But that means there's a problem, because this radiation, as I explained already, is extremely bright. So this radiation is going outward and is impinging on the gas trying to fall towards the black hole, and is trying to, by radiation pressure, I mean, radiation has associated pressure because the photons hit the infalling electrons and impart their momentum to the electron, and they basically try to stop the accretion. Now, this is a runaway process if you think about it, because if you try to say, well, I'm trying to feed the black hole quite rapidly because I'm in a hurry, I want to make a big black hole out of it, that means you increase the luminosity of this black hole, which means you suppress the growth rate even more. So I like to invoke here the analogy that this gives you a universal maximum feeding rate, because which is very similar to trying to feed your nephew, because if you try to feed the baby too fast, I mean, if you feed it slowly, the food goes in. If you try to feed it too fast, at some point it doesn't go in. So this is the same with black holes, except here the radiation is the problem. And the bottom line here is that because of this limitation from radiation, it's not possible to take a solar mass black hole in the early universe and by 700 million years grow it to 1 billion or more solar masses. This is about 30 or sometimes 100 times too small, the resulting maximum black hole mass. I'm going to skip these equations, how this limiting rate is calculated. It's actually quite simple. I'm happy to explain it if people ask me to. But I just want to say there is a way to avoid this, which is, and I won't have actually time to go into details of this particular conclusion, but we've come up with a solution to this, which says, well, if you feed the black hole at extremely high rates, which are much higher than this limiting rate would be normally, then what happens is the radiation cannot escape. So this here is demonstrating a slice where here's a black hole. This is a cross-section of the disk where it's trying to accrete. So this is the swirling motion that in my previous slides. And then this shows that the photon, which is generated over here from the hot gas in the innermost part of this accretion process, this is a photon that's trying to go out. But if this gas here is building up extremely rapidly, then this photon keeps hitting the electrons and has to random walk out of the cloud. This is actually a mathematical random walk problem. And then the essential point is that if this gas is extremely opaque and is flowing inward faster than the photons can diffuse outward, then this black hole radiation cannot escape. It just basically gets completely trapped. And the photon just swallows all the material that's fed to it. And it also swallows the photons that itself generated. So that's our possible solution. And again, I will come back to in a few minutes how we might decide what is the universe actually doing, whether this is actually happening. But let me go back to the other way, which is, well, you don't really maybe have to grow them so fast. You just have to have lots of mergers between black holes. So I should say that this is actually a very natural idea because let me just show this slide back that I skipped. So we have another very basic understanding of our universe, which is all the density in the universe congregates due to gravitational instability into lumps. This is an image from a simulation of how the density distribution of the universe looks like. So one of these lumps might be one of the clouds that hosts a black hole. Here's another one, here's another one. And as the universe evolves, these lumps tend to attract each other and merge. And that's how galaxies form, by subsequent mergers. So that begins at the earliest times. You form these collapsed proto-galaxies with just a few stars, which leave black hole remnants, but then they, over the course of the evolution of the universe, collide and merge and make bigger galaxies, eventually something like the Milky Way. So during these mergers of galaxies, you could possibly have mergers between the black holes sitting in these clouds. And by the way, I mean, there are beautiful images of merging galaxies that we've detected with many telescopes. So this is, again, uncontroversial. So here's the problem with this scenario. Well, I already told you that physicists think of a black hole as just a funnel distortion in space-time. Now, if you have two of them close to each other, then these two black holes will orbit one another in a, let's just assume for simplicity that they're going around in a circle. Then these two funnels are no longer stationary. So that's why they generate the so-called ripples in space-time, so-called gravitational waves, which keep propagating away from the binary black hole. And we know that this process extracts energy from the binary because these ripples in space-time carry off some energy, and that energy had to come from somewhere, and that energy comes from the binding energy of the binary black hole. Now, that's very promising because if you radiating effectively, getting rid of the binding energy, that means the binary has to be getting more and more compact and spiral inward. And this is completely inescapable process, and it would eventually make the black holes merge. And in fact, as you know, not only is this theoretically completely uncontroversial, these gravitational waves were detected. So we know stellar mass black holes. I'm gonna skip the details of this discovery. I'm sure you all know that 2017, the Nobel Prize was given to the LIGO experiment for discovering the gravitational waves. For my talk, the important point is that these mergers can happen in principle, but once the black holes become larger, actually I'm gonna skip this also and just tell you the issue. So the issue here is that the black holes, in order to merge in a reasonable time, meaning within 700 million years, or actually much less if you want to have several mergers, they already would have to be extremely close to each other. Otherwise, these gravitational waves are very weak, and they wouldn't take much longer than the age of the universe to cause a merger. So just for reference, if you have a 100 solar mass black hole and another 100 solar mass black hole, and you want just the gravitational waves to drive them together to merge within 10 billion years, which is the current age of the universe, they will have to start from a separation which is 0.2 AU, which is 5 times smaller than the Earth-Sun distance. So that's just very small. And the question is, and that's not natural. Why should two black holes randomly find each other so extremely close to each other? And that just doesn't happen naturally. So you need something else to create compact pairs of black holes. And so here our solution is based on the fact that there is gas around these binary black holes when they're much more widely separated. And I just show a movie here. So this is a hydrodynamical simulation which shows two black holes, and this orange and black and blue stuff shows you the view of the gas distribution. This is assumed to be in a disk. And this is very analogous to the cartoon pictures I showed before, where there's only one black hole and this accretion disk is swirling around it. Here there are two black holes instead, and this simulation shows many interesting things. There's a cavity, there's all these streams sloshed around, but the most important part of this for our story here is that you can obviously see that this gas density here is not symmetric. It's very asymmetric, so it exerts forces on these black holes back reacting on the black hole. So this dense lump over here will pull more on this black hole than this black hole. This dense lump over here will also pull more on this than this. So these asymmetries change the orbit of the black holes. And what we've shown is that these forces from the disturbed disk on the binary can help extract the binding energy of the binary and push the black holes together to a small distance, after which gravitational waves can take over. So I think I'm gonna just make the point that therefore there are two ways to start with small black holes and make a very large one. Both had some problems. We think we can circumvent both problems with different ways. So I think the last question you should ask, which I'm going to skip here, is how will we tell which of these is correct? And so in general, I think there are two ways. One is detect the mergers between them, just like LIGO did, or just observe these big black holes when they're trying to grow by accretion and become big enough. And so essentially extend the observations of distant quasars to much earlier times and much smaller black holes. So the first of these will be possible by LISA, the Laser Interferometer Space Antenna. This is currently basically has been funded. It's a large mission by the European Space Agency, and it's planned to be launched in 2034. It's very different from LIGO, because LIGO is an instrument that's sitting on the Earth. LISA will be launched into space. This here shows you a gravitational wave source. This here is the sun. This is the Earth. This is the moon. And this shows you that there are 3 test satellites revolving around the sun, trailing the Earth. And there are lasers between them. And they measure the distance in this triangle, and the small ripples coming from massive black holes in the early universe will be detectable by this telescope. Well, actually, we should call it instrument. It's an interferometer. And that can tell you how many mergers took place between what kind of black holes in the early universe. The other way to proceed is, if there were no mergers, you will not see anything with LISA. But then you must see black holes emitting radiation in the process of their growth at some point. And that could be discovered by the James Webb Space Telescope, which is actually supposed to be, originally was supposed to be have been launched by 2018, but it's been delayed. It should be launched next year. So stay tuned. I think I will stop here and could stay for another few minutes for questions if people have any. Thank you.
Can you explain why the asymmetries in the density arise?
Yeah, that's a very good question, actually. You mean in the simulation that I showed, this one? So this one, yeah. I don't know about this. Yeah, so that's actually an excellent question. And we don't fully understand. We cannot explain this with some equations and theoretical analytic formula. This is a result from the simulations. But I can tell you one thing that we understood, which is, you see this cavity is very, so I do think this is actually an excellent question, because you would naturally have expected that this cavity should have a mirror symmetry, since these are 2 equal mass black holes. So there's no reason for this part to differ from this part. But what we found is there's an instability. So you see that these streams of gas, they're peeled off. And this is actually very simple physics. It's basically textbook physics of just gas on starting from Keplerian orbits around the binary. So you see that gas is pulled off from the stream from this cavity and is trying to fall into the black hole, but you can see that a lot of that gas doesn't get captured by the black hole, it's flowing outwards. And what happens is this stream hits the cavity wall and makes this cavity denser, and then this lump slowly goes around and modulates how strong these streams become. And what you see is if there's initial tiny asymmetry, then one of these streams becomes stronger than the other, causes the cavity wall to become distorted, and that causes that stream next time to be even stronger. So there's a runaway process. Even if you start with a completely symmetric disk, of course, if it's exactly 100% symmetric, then it will remain symmetric. But even if it has an absolutely tiny deviation, it will run away and cause this lopsidedness. So we could demonstrate this with the simulations, and but there's no analytic formula that predicts this asymmetry.
Is it dependent on the direction somehow? If I reverse the direction of the rotation of these black holes around each other, will this density shift to the other side in some sense?
So I think it's so there's, I think that's basically an arbitrary. The direction of this black hole is just arbitrary. This is just a simulation. If I look at it from the other side, the same simulation will predict what happens in the opposite direction. So yes, in principle, if you start with an identical configuration and start the black holes going the other way, you should have a mirror image of your previous simulation. But I should just emphasize that that's probably...
Dr. Haiman?
I should emphasize it's kind of more random. There's a tiny fluctuation somewhere in the disk, which will cause this lopsidedness. Yeah, go ahead. Go ahead.
Dr. Haiman?
Sorry, I cannot hear anything. I think there's some connection issue with whoever is asking the question. Maybe you should type the question in the chat window.
I think there could be some network issue with him.
Okay.
So I had a question. Could you explain about the radiation pressure again that causes the massive black holes? And you said talked about a limit on that as well.
I'm happy to do that. Do you mean just the concept, or do you want to go through the slide with the equations?
You could go through the equations as well. That.
Okay, then I think that. So I'm happy to do that. It will take a minute or two. So the idea is that this is just a very simple spherical setup. So you have a black hole here, gas is flowing in at some rate, which is dm dt. So this is a rate, mass per unit time flowing towards the black hole in a spherical configuration. Now, the black hole's mass will be growing at a rate which is just some constant times this inflow rate. So this represents a constant which says what fraction of every particle's rest mass goes into the black hole. And the black hole luminosity will be 1 minus that. So 1 minus this fraction, dm dt times c squared, must have been deposited somewhere else. So it's some energy which didn't fall into the black hole. I mean, the microscopic physics of this is, for example, gravity accelerates the particles falling in to near the speed of light. So they will radiate. Even if they don't collide with each other, they will radiate due to free so-called Bremsstrahlung radiation. In reality, they will collide with each other and cause hydrodynamical shocks in high temperature, and there will be thermal emission. So this 1 minus epsilon dm dt c squared is effectively luminosity, which will have to come out. And then the idea is that there's radiation pressure because of this luminosity, which is proportional to the luminosity divided by 4 pi r squared. This is the flux. So there's a luminosity emanating from here. Then at some further radius r out here, there's a flux L over 4 pi r squared. And therefore, there is a pressure exerted on an inflowing particle, which is proportional to this flux. And I just don't bother here with the constants. But I mean, the process, I don't know if you learned this already, but Thomson scattering is a process where photon hits the electron, transfers its momentum. And there's a cross section for that. But the net force on inflowing gas is proportional to the flux. And because of the luminosity goes like m dot over r squared, this outward force goes like m dot over r squared. Now, the gravitational force, which is inward on the same piece of gas trying to fall in, is just gm over r squared. So now we have an equation which says this radiation is an outward force, this gravity is an inward force. So this has to be at most the same as gravity, otherwise it's inconsistent. If the total force is pointing out, if the net force, gravity plus radiation, is pointing outward, you cannot have accretion. So the largest rate is if you equate these two. So you can see both go like r squared, 1 over r squared. So then when you equate these two, you get an equation that just says m dot black hole is a constant times m black hole. And I just didn't bother with this constant, but they have, in these constants, there's Newton's constant and the Thomson scattering cross section and the speed of light. So everybody knows the solution of this equation, right? If m dot is a constant times m, then what is m as a function of time? Well, that means m is an exponential. So you can take the original black hole mass, in our case, let's say 100 solar masses, and then the largest mass later on that you can get to is an exponential times that. So we'll go like t over some time constant, and that time constant again is just created out of a product of g and c and the Thomson cross section, and that's why you can predict the growth rate. So we know that if this is 100 solar masses, this time scale is about 40 million years. This is the e-folding time scale, and this is 700 million, which is what we want to. This is in our case, we want to wait for 700 million years, and that's how you get this mass that's too short, too small. That's it. I hope that was simple enough.
Yes, thank you. Also, there's a question in the chat.
Okay. So the question from Piyush Mohit is, can we blame the symmetry to chaos theory? What exactly does pressure of gas in free space signify? If actually caused by collision of a gas with container gas, what kind of pressure exists in space? How do we come to the conclusion the rate of mass change of black hole very linearly with the rate of absorption of gas? So these are actually 3 questions. I think I'm happy to. First of all, a chaos theory probably not necessary because because I think this is a nonlinear runaway instability. But in the sense that tiny deviations lead to very different outcomes, it could be chaotic. So we have not looked into that question. I think by chaos you would mean, suppose the little tiny instability, a symmetry in the simulation which triggered this macroscopic big lopsidedness. Suppose that the initial tiny difference was just a little bit different. Would the end result with the lump be very different? I suspect not. So I don't think there's chaos here. The second question, what does pressure of free space mean? So I'm not talking about anything exotic. I'm talking about a gas cloud, and inside the gas cloud there is pressure internal to the gas cloud. I didn't talk about free space. I'm talking about internal pressure of a collapsing cloud. And then how did we come to the conclusion that the mass change of the black hole very linearly with rate of absorption? I think you're talking about this assumption here. And
Yes.
yeah, so that's actually an excellent question. We don't actually really know that for sure, but there is an expectation that we know this number epsilon. And that comes from, let me illustrate it actually with my slide. What happens if you think of this fluid is falling towards the black hole and is orbiting very stably. If you've taken general relativity, you know that there's a particular aspect of this potential, which is there's something called the innermost stable orbit. So if you had no radiation at all and you put some gas, or in fact, you can just think of a test particle, you put it over here, it's going to eternally go in a circle. And the idea is that as long as it's doing that, you can eventually, if it's gas, you can extract its energy by slowly eroding all its kinetic energy and due to collisions with neighboring gas. So the idea is that this coherent disk whose annuli have friction with respect to one another and slowly heating up the gas and converting everything to radiation. Then the idea is that there is a particular radius, let's say, just for schematic illustration, let's say this circle, this black circle here, is a special place in the Schwarzschild metric, which is the word describing this potential. Inside that circle, there's no stable circular orbits. So if you put some stuff in here, it's unable to go on. You can't see that from this picture, but in general relativity, you find if you put a particle over here, there's no stable circular orbit. It will just tend to radially fall into the black hole and will not suffer all this laminar motion and coherent friction that can do outside that circle. So the idea is that you can extract the energy, which is Gm over R, where R is the radius of this critical circle. And that corresponds to about 10% of the rest mass. So that's the explanation. It's consistent with observations. There's a few cases where we can measure the black hole mass. I won't go into that now because it's too complicated to explain. But there are several quasars where we know the black hole mass and we also know the luminosity, and that's consistent with this 10% radiative efficiency. So I think, unfortunately, I need to go. I have some other engagements.
I suppose there are no more questions as well from our side.
Okay, good. Thanks again for, hope you learned something.
Yes, thank you. This has been a very interesting and always informative lecture by you. We thank you for accepting our invitation, and I also thank everybody who attended the lecture. Thank you.
Yep. Thank you. Bye-bye.